So for this question, we have a law of conservation of energy question. Okay, it's saying here that we're going to forget about, friction and all of that kind of stuff. Well, it doesn't really outright say that, but we have to assume that. Okay, so we have human cannonball in the circus is shot at a speed of 21 meters per second, 20 degrees above the horizontal, from a platform that's 15 meters above the ground. All right, so acrobat has a mass of 56 kilograms. What is his gravitational potential energy relative to the ground when he is at the highest point in his flight? Ignore the effects of air resistance. So, law of conservation of energy question. So here's what we have to understand. This person is being shot at an angle, which means they're going to go higher than this 15 meters. Everybody okay with that? Can I calculate how much higher than those 15 meters? I can. Okay, I can calculate that because I can calculate how high they would be, or what their maximum height would be, using projectile motion. Okay, so that's the next thing, or the first thing, okay, that I want to do is calculate their maximum height. So I'm going to break this down to a projectile motion problem. This is 20 degrees. Okay, this is 21 meters per second. Okay, and I actually need both sides of this triangle. I need their horizontal velocity and their initial vertical. Why do I need both? When they're here at their maximum height, are they still moving? But they're moving horizontally. I need to know how fast they're moving horizontally at that point. Okay? That way I can figure out how much of their mechanical energy here is kinetic and how much of it is potential. All right, so I could do this kind of one way or the other here. I can calculate their initial mechanical energy right now, which probably isn't a bad idea. Okay, so that's going to be m times g times h plus 1/2 mv squared. These will be our initial values. Okay, so that'll be the 56 kilograms times 9.81 times their height, 15 meters, plus 1/2 times 56 times their initial speed, which was 21 meters per second, and that has to be squared. All right, everybody with me on that so far? Okay, so can we do that calculation pretty quickly? All right, so let's punch that one in real fast. Okay, so mass times gravity times their height plus 1/2 times their mass times their speed squared. All right, so this is their total mechanical energy initially. It's also their total mechanical energy, right, anywhere, okay? Anywhere along that flight path, that's the amount of mechanical energy they have. It's how much the cannon gave to them, okay, for the fact that it was fired and was 15 meters above the ground. That's their mechanical energy anywhere along the flight path, and that's an important thing for us to remember, so it's an important number for us to have, okay? That is, 20,588.4 joules. Okay, so they want me to calculate now their potential energy here. Everyone okay with that idea? All right, now, their potential energy here can be determined the same way we determine any other mechanical energy anywhere else. Okay? So I've got mechanical energy is the sum of the potential and the sum of the kinetic. I already know the mechanical energy because I calculated it here. Okay? But this is why we needed their horizontal speed. Okay? We needed the horizontal speed here because we're going to need it to calculate their kinetic energy so that we have this value and this value, and then we can work backwards to calculate, okay, their potential energy at that point. Okay? The other way to do this would be to calculate their maximum height using projectile motion, and then figure out what their potential energy would be there, plus the potential energy of the 15 meters, okay, and get the total. Either way will work, it's just whether I'm looking at it from a potential energy standpoint or a kinetic energy standpoint. Okay? But I want to use this because that involves using this number that I calculated earlier. Okay? So I'm going to calculate the horizontal velocity of the cannonball, human cannonball. Okay? So it's what side of this triangle? Adjacent or opposite? Okay, so what trig function am I using to get it? Cos. All right. So we're going to get V horizontal, okay, by going cos of 20 degrees times our hypotenuse, which they told us was 21 meters per second. Okay, so our horizontal velocity is 19.73 with all those decimals that we won't write but keep in the calculator. All right, what was I going to use this number for again? Right, to get the kinetic energy at their highest point in the flight. All right, so that's my next step then. Use this number in calculating the kinetic energy. So we're going to have 1/2 mv squared. Okay, so that'll be 0.5 times 56 times our 19.73 squared. But this time we'll use all the decimals because we kept them here. So 0.5 times 56. Whoops. Our answer squared. Okay, so there's our kinetic energy, 10,903 joules. And of course, we're going to keep all the decimals, I'm just not writing. All right, so now I know the kinetic energy, and I know the mechanical energy because I calculated it the moment they were fired. And we know that it's the same all the way through the flight. So I'm going to get the potential now by doing what with the two numbers I have? Subtract it, exactly. All right, so I'm going to go mechanical energy minus kinetic energy, okay, equals our potential energy. All right, so okay, we'll have our 20,588.4 okay, minus our 10,903 with all the decimals, of course. 20,588.4 minus our answer from the last one. All right, so we're looking at 9,684.8 joules worth of potential energy. Everybody all right with what we did there? Okay, could I calculate their height right now? Would that be a logical next thing for them to ask? Sure it would. Okay, so how would we do that now that I know this number is potential energy?
Manipulate the potential energy just equation to find out.
Exactly, yeah, we know this. Potential energy equals m times g times h, mass times gravity times height, right? We can very easily calculate their maximum height now, okay, by going 9,684.8 divided by 56 times 9.81, so over m times g, okay, that'll give us our height. Okay, they didn't end up going that much higher, did they? Okay, they were launched from 15 meters above the ground. But their maximum, now they're saying that at that point, their maximum height, they're only 17.6 meters above the ground. Is that okay? What was the angle they were launched at again? 20 degrees. Not very much of an angle, right? They're not going to get much higher. You know, it's like this. Okay? They're not going to get launched very high from that. And if you've ever seen the human cannonball at the circus, it was never about how high they could launch them. You're in the big top, right? You're not looking for height. You're looking for distance. Okay, so they're firing them more this way as opposed to this way, right? And then, of course, them safely landing in the net on the other side and all of that stuff. Okay, now the other part of this question says, if the net in which he lands is 2 meters above the ground, how fast is he traveling when he hits it? Okay, do I need any of this intermediate stuff that I did in order to answer that? No. Okay, I already know his mechanical energy when he hits the net. It's that 20,588 already calculated, right? Conservation of energy. It's not changing at any point along this flight. So all I have to do is say that's his mechanical energy when he hits the net. Because I know his mass and his height, I can find his potential energy, okay? And I can find then his speed, okay, from there. So this is going to be like the roller coaster questions we did before, okay? We're going to say his mechanical energy equals m times g times h final plus 1/2 mv final squared. Okay? Essentially here we're saying EI, which we already know, equals, what's this say? EF, right, okay, law of conservation of energy. All right, I want to find VF. What do I do with this right now? Subtract it over to the other side. Okay, so my mechanical energy minus m times g times h equals 1/2 mvf squared. Looking for VF, what do I have to do with the half and the m? Divide them over. And then what? Square root. Okay, good. You guys remember this from last week. Okay, so we've got our 20,588.4 joules minus mass, 56, times gravity, 9.81, times height, 2 meters, divided by 1/2 times 56, all square rooted. Okay, that should give us his speed when he hits the net over there. So 20,588.4 minus 56 times 9.81 times 2 divided by 1/2 of 56, and then we, whoop, I don't need the decimal there. I need that there. All right, and then I square root that, and that should give me how fast he hits it at, 26.4 meters per second. Okay, is that pretty fast? It is. Yeah, okay, it is pretty fast. We're putting that into kilometers per hour. It's 95 kilometers an hour. I would hope that net is sufficiently tight so that I don't travel the additional 2 meters to the ground after I hit it. Okay. All right, is that ringing a bell for everybody? Okay, we've seen a bunch like that. All right, so our next thing here is a pendulum. We'll talk more about this when we get to the last unit where we talk about simple harmonic motion. Okay, but a pendulum is still an example of conservation of energy. All right, so this is what happens when you cut money from education. Okay, you get an old roll of athletic tape tied to the drawstring from my hoodie for a physics demo. It works. It's not pretty though. All right, so if I've got this thing hanging right here, okay, it can't fall any further because I'm holding it. Does it have any energy? No. Okay, there's no mechanical energy. Can't fall any further, not moving, okay, no kinetic, no potential, thus no mechanical energy. What about now? Has potential energy, and thus it also has mechanical energy. Okay, how did it get that? What did I do? 4-letter word. Work, yeah, okay? I did work. I lifted this, I pulled it against the force of gravity to a height higher than what it was at before, okay? Doing that work imparts it now with potential/mechanical energy. If I let this go, what's going to happen to it? All right, it's going to fall along the arc, and it's going to do what as it's falling? Accelerate. Okay, it's going to turn it, what kind of energy here? Potential into kinetic. Will it be conserved? Assuming it's a perfect pendulum, which of course it is. You will now cluck like a chicken. No, it didn't work. It never works. I can never hypnotize anybody. Okay, this thing's swinging back and forth. Okay, swinging back and forth, converting potential energy into kinetic. The amount of mechanical energy it has should technically be equal at all points along that arc. Okay, all points along that arc have the same amount of mechanical energy. Here, it's all potential, and down here, it's all kinetic. Okay, so that's the thing we have to remember about a pendulum. Okay, it's very much like a roller coaster. Okay, at the highest point, most of its energy is potential. At its lowest point, most of it is kinetic. Okay, that's just the way mechanical energy conversions go. Okay, so if we have this ideal pendulum and it's on this 2-meter long string, okay, it's pulled sideways and released. The highest point of the swing is 25 centimeters above the floor. Okay, the lowest point of the swing, the pendulum bob, is 5 centimeters above the floor. Okay, and the mass of the pendulum bob is 250 grams. Am I interrupting you guys? Thank you. Okay, what's the mechanical energy of the pendulum relative to the floor when the bob is at its highest point? Okay, how do I do that? At its highest point, we said it only had potential energy. All right, so can I calculate its mechanical energy there? Okay, so remember, mechanical energy is always the sum of an object's potential and kinetic energy, but we already said its kinetic energy at that point is, at its highest point, is 0. It's not moving there. Okay, so it can't have any kinetic energy. So all I have to do is to go m times g times h, and I've got the mechanical energy of this pendulum anywhere along the arc. But this is the easiest place to calculate it. Right? So 0.250, because they told us it was 250 grams, times 9.81, and then we've got our height, which they said is 25 centimeters. What does that need to be in, though? Meters. Okay? This is the kind of question that tricks people if I put it on a test. Okay? If I'm, a jerk and I put in grams and centimeters instead of what you're used to, which is kilograms and meters, some of you would forget to convert it to the proper units. And then you're not getting joules, you're getting either hundredths of a joule or thousandths of a joule, okay? And you're not getting the right answer. All right, so we've got 0.25 meters. So 0.25 times 9.81 times 0.25. All right, so this thing doesn't have very much energy, does it? Less than a joule. And that kind of makes sense. This isn't very heavy, okay? Because it doesn't have a lot of mass, and because it's not very high, it doesn't really have a lot of ability to do work, right? I mean, if this thing hit me, it wouldn't hurt, would it? All right, so 0.613 joules. All right, now, this is the kind of thing that people, remember last week we were talking about how you want to be efficient when you're writing a test with your time? This is one of those questions where knowledge is power and gains time. Okay? So we just calculated the mechanical energy relative to the floor at the highest point. What's the mechanical energy of the pendulum relative to the floor when the bob is at its lowest point? The same number. And if you recognize that, you don't go through all the trouble of recalculating that and then looking at your calculator and going, oh, I just spent 5 minutes recalculating a number I already calculated. Okay? This is why it's important to have that understanding of the law of conservation of energy. If I understand that, I don't have to spend a lot of extra time on this question. Okay? And I've given multiple choice questions that look just like this. Okay? This is how it starts. I give all this information, I ask you to calculate this, and then for part B, for the question, I would say, for question 1, it would be calculated here, and then question 2 would be, all right, what is it at this point? And people go about calculating it again when it doesn't require any other calculation. Okay? And that second calculation would be more involved because when it's at its lowest point, it's still 5 centimeters above the floor, so it's got potential still. And now it's moving, so it's got kinetic. And here's the real kicker. They don't tell me how fast it's going. So I would have to go through some sort of convoluted calculation in order to figure out its kinetic energy because I don't know its speed at that point. Okay? But if I understand law of conservation of energy, I save myself all of that work and trouble. Okay? All right, part C. What's the kinetic energy of the bob at its lowest point? All right. Can I calculate that rate? I can't. Okay? Because I already know its mechanical energy, and I know that at its lowest point, mechanical energy is still this. EP plus EK, and I know its height, so I can calculate the potential. All I would have to do to get the kinetic energy is, since I already know EM and I can calculate EP, what would I do with EP? Subtract it over the other side, okay? So we'd have our 0.613 minus, okay, our mass, which was 0.250 times 9.81 times 0.05, okay, 5 centimeters, 0.05 meters, okay, that'll equal EK. Alright, so the kinetic energy there at the lowest point, 0.4905. Would make sense that most of the energy at that point would be kinetic. That's its lowest point, it's where it's moving the fastest. Okay, so 0.4905 of the 0.613 is kinetic, so the majority of it is kinetic at that point. Okay. Alright, could I now calculate the speed? Because that's the next thing they want to know. What's the speed of the pendulum bob at this point? Okay, well I've just calculated its, what did I calculate here? It's kinetic energy. Okay, do I know its mass? I do. Okay, so I can calculate its height now, or sorry, its speed now. So 0.4905 joules is my kinetic energy. Okay, and I know that kinetic energy equals 1/2 mv squared. So if I want to solve for v, I divide both sides by half of m and square root. Okay, so we got the square root of our kinetic energy, 0.4905 joules, divided by 1/2 times the mass, 250 grams. Okay, and we've got our right, so it's moving at just under 2 meters per second. Okay, that is the lowest one. Okay, have any of these required like really in-depth, complex calculations? Okay. Not really. I mean, this manipulation was probably the toughest thing mathematically to get here. Okay, but did all of them require that level of understanding, that convoluted reasoning that we've been talking about the whole unit? Okay, being able to see what's going on in your head and see the connections between things. Okay, that's the most important part. The math will take care of itself. All right, I want you guys to try one here. I want you guys to try number 2. I'll make it way bigger so you can read it. Okay, so on number 2 here, we got a model rocket, mass 3 kilograms, fired so that when it is 220 meters above the ground, it is traveling at 165 meters per second. At that point, it runs out of fuel. Okay, if it runs out of fuel, from this point on, energy is, okay, if it doesn't have an engine anymore, can any work be done anymore? Okay, so after this point, energy is conserved. Okay, its amount of mechanical energy after this point remains the same until it re-encounters the ground, because there's nothing to do any work on it since the engine has run out of fuel. Everyone follow me there? That's why they tell you that. Okay, all right, so at that point, the fuel runs out, rest of the flight is without power. Assuming there's no friction, okay, so it's the law of conservation of energy, okay, all potential energies are measured from the ground. What's the mechanical energy of the rocket? 220 meters above the ground, remembering this number here as well, okay? And B, when it reaches its highest point, what will its gravitational potential energy be? This is another one of those ones that you can save yourself a lot of work if you understand this, okay? And for part C, okay, how far above the ground is the rocket at its highest point? I made it too big and now it doesn't fit. Hang on, I'm gonna make it just a tad bit smaller. Okay, I'm gonna give you a few minutes. See how you do, and then I'll walk through part A, and then give you a few more minutes, walk through part B. Okay? But give you guys a little bit of time to try that one on your own. Here. So, it's asking us to calculate mechanical energy, which we know is the sum of an object's potential and kinetic energies. This is a rocket that is 220 meters above the ground, moving at 165 meters per second. Does it have potential energy? Does it have kinetic energy? It's got both. It's moving and it's above the ground, okay? So neither one of these are 0. All right, I have formulas that can calculate them both. M times G times H initial plus 1/2 MV initial squared, okay? I have all those numbers. They told me the mass is 3 kilograms. I always know gravity. They told me the height's 220. They told me the speed's 165. So I have all of the numbers involved in this formula. All I have to do is plug them in. So 3 kilograms times 9.81 meters per second squared times 220 meters. That'll give me my potential energy, okay? Plus 1/2 times our mass, 3 kilograms, times our speed, 165 squared. All right, so that's going to calculate my mechanical energy, okay, at that point. Not only at that point, but
The whole trip.
over the whole trip. Right. Okay, so 3 times 9.81 times 220 plus 0.5 times 3 times 165 squared. All right, so we have 47,312.1 joules worth of mechanical energy. All right, now that's part A, and we have how many significant figures here? 3. Okay. This has 3 significant digits, this has 3 significant digits, this has 3 significant digits. So my answer shouldn't be this, it should be 4.73 times 10 to the 4 joules. Okay, remember someone asked about this last week. When I'm answering a question, if I answer part A and then I use my answer for part A for another part of the question, do I use the rounded value or do I use the non-rounded value? And we said we use the rounded value. Okay, got our final answer here to the right number of significant figures. All right, so that's part A. Part B, when it reaches the highest point, what will its gravitational potential energy be?
Same thing.
Same thing, that number. Why? Okay, because the mechanical energy is the same throughout, and when it's at its maximum height, since it was shot straight up in the air, what's its speed at its highest point? 0, right? I throw something up in the air, at its highest point is where it changes direction. Okay, its speed at that point is 0, so it has no kinetic energy there. Okay, it's not like the human cannonball who was fired at an angle. Okay, this was fired straight up. So at its highest point, it has no kinetic energy, so all of its mechanical energy is potential at its highest point. Everybody okay with that? All right. If I remember that kind of stuff, a little bit of stuff from Unit 1 about projectiles, okay, and a little bit of stuff from here about conservation of energy, do I save myself a lot of work? Yes, because you could calculate its maximum height, figure that out, and then do this calculation over again and arrive at exactly the same number. Would that be futile? Not futile, but a waste of time. Okay? We wouldn't want to waste time calculating a number we already have. All right, for part C, how far above the ground is the rocket at this point? Can I calculate that? I can, because I just wrote down that this number here represents my potential energy at the highest point. And I know what the formula for potential energy is. So I can say that 4.73 times 10 to the 4 joules equals m times g times h. Okay. How do I get h by itself? Divide mg. Okay, so that'll be divided by 3 times 9.81. All right, that'll give us our height, okay, which should come out to 1.61 times 10 to the 3 meters, but we'll double check it. Okay, so, yep, 1.61 times 10 to the 3 meters, right? So it is exactly 1 mile above ground level. Okay, 1.607 meters is 1 mile. You may. Okay, last part of this question. wants to know when it hits the ground, what is its speed? I'm going to give you a few minutes. I want you guys to try and calculate that. Okay? It shouldn't take very long because it's one simple calculation. Okay? In order to answer this question, what two things do I need to understand? The potential energy will equal 0. Okay, so all of the rocket's mechanical energy will be kinetic when it strikes the ground. That's the first thing I need to understand. What is its mechanical energy when it strikes the ground? That number. Energy is conserved. That's how much potential energy it had at the highest point. That's how much mechanical energy it has at any point in the flight. We said that like 5 times, okay, at the very beginning of this question. Okay, when it ran out of fuel, that's how much mechanical energy it has. When it was at its highest point, that's how much mechanical energy it has. When it hits the ground, that's how much mechanical energy it has. It's just now it's all kinetic. Okay, if I understand that, then it's a simple matter of saying this. 4.73 times 10 to the 4 joules equals 1/2 mv final squared. Okay? All of its mechanical energy is kinetic. The instant it strikes the ground, I can calculate its speed there because I know its mass. Okay? So I divide both sides by half of m and square root. Okay? So as long as I have those two little things and I understand those two little things, okay, this is a pretty easy calculation. Okay? So when I punch in my numbers here, okay, I'm going to have that square rooted 4.734 okay, divided by half of the mass, so 1.5 because it was a 3 kilogram rocket. All right, so it's moving at 178 meters per second when it plows into the ground. Is that making some sense? Ringing a bell from last week? Okay, I want you guys to try number 3. Okay, this is one like you would have done in Science 10 for sure. Okay, so give you a few minutes. They're on number 3. Okay, let's have a look at least the first part of this one here. Well, it's all of it, I guess. All right, so we got this situation here. Okay, we've got the roller coaster on top of its first hill, and then they're asking us about the kinetic energy at the top of the second hill. So we know this first hill is 85.0 meters high. Okay, we know the second hill is 64 meters high. Right? We also know that the first hill, the trolley has a speed of 0.2 meters per second. And we know the mass is 840 kilograms. Okay, there you want to know what the kinetic energy of the trolley is at the top of the second hill. All right. What do I need to understand about these 2 points? They have the same mechanical energy. My mechanical energy at the initial point is equal to my mechanical energy at the final point. Okay? That's the first thing I have to understand in order to solve this problem. Right? Then I can start doing this whole chestnut. Okay? EI equals EF. Right? That's going to mean the potential energy initial plus the kinetic energy initial equals the potential energy final plus the kinetic energy final. Now, they're not asking me to calculate the speed there. They just want the kinetic energy. So this is actually a little easier. Okay? If I just want the kinetic energy final, what do I have to do with the potential energy final? I want to get this by itself. What do I do with this? Subtract it over to the other side. Okay, so I'm going to have EP initial plus EK initial minus EP final equals my kinetic energy final, and that's all they're asking for. So I'm just going to go M times G times H initial plus 1/2 MV initial squared minus MG H final. And that'll give me what I'm looking for. Can I cancel masses here? I can't. Why not? What I'm looking for contains mass. Right? If I'm looking for an energy form, I have to have mass in there. If I was just looking for a speed, the mass wouldn't matter because all things would fall at the same rate and the mass wouldn't make any difference. But in this case, because I'm looking for the actual energy, mass does matter. If this was, you know, a roller coaster trolley that was twice as heavy, it would have twice as much energy. Right? Everyone kind of follow me there. So I can't cancel the masses, and all I have to do is plug in my numbers. So it was 840 kilograms. So 840 times 9.81 times 85 plus 1/2 times 840 times 0.2 squared minus 840 times 9.81 times 64. That'll leave me with my final kinetic energy. 840 times 9.81 times 85 plus 0.5 times 840.2 squared minus 840 times 9.1 times 64. All right, so my final kinetic energy is 1.73 times 10 to the 5 joules. Okay. Could I very easily have asked you also what the speed of the car was at that point? And you guys wouldn't have any trouble with that either. Okay. How many people have ever watched pole vault before? Okay, so in pole vault, you are trying to convert kinetic energy into potential energy. Okay? You do that by carrying a long fiberglass pole and running as fast as you can towards the bar. At the last moment, you plant the pole. Okay? And all of your speed, your kinetic energy, is converted. But it's converted into a different kind of potential energy. When you plant the pole, what happens to the pole? Ideally, it should bend. Okay? If it doesn't, it's because you have the wrong side facing up. Believe it or not, there's a bendy side and a non-bendy side to a pole vault pole. Okay? I've seen many accidents due to the fact that a pole slipped in sweaty palms. Okay? So, plant the pole the right way, the pole will bend and it will convert your kinetic energy into elastic potential energy, the bending of the pole. Okay? If you bend the pole effectively, once you leave the ground, the pole will throw you into the air, taking your kinetic energy, okay, and turning it into gravitational potential energy, or actually taking its elastic potential energy and turning it into gravitational potential energy for you, okay, throwing you up into the air, okay, and then over the bar, hopefully. Now, at your highest point, just when you are going over the bar, how fast are you going? Since you've been thrown vertically into the air. 0. Okay? So at that point, all of your energy is potential. Right? So what we're looking at in this question is we're comparing the kinetic energy, okay, mechanical energy that they have on the ground to the potential energy they have as they are going over the bar. And we're trying to use that to calculate how high the bar is. All right? So we'll give you a few minutes and see if you can calculate that one. All right, so we already did part B. We talked about the energy changes that are going on here. Kinetic energy of the speed of the approach being turned into elastic potential energy in the pole and then into gravitational potential energy as you go over the bar. Okay? The reason we do that is because we need to understand, okay, what forms our mechanical energy is going to be in at the 2 points that we're comparing. At the first point we're comparing, we obviously have kinetic energy because she's moving at 8 meters per second. But do we also have some potential? Even though her feet are on the ground, it does mention that her center of mass is 0.850 meters above the ground. Okay? I mean, if I'm standing on the ground, I still have potential energy because I can still fall. Okay? I can still fall down from this height. Okay? And there's a fair amount of energy involved in that because of my mass. Not because of the height, but because of my mass. When you think about it, elderly people, okay, they can fall from this height just from standing or even from sitting and break some of the biggest bones in their bodies, okay? Because there's still a fair amount of energy, even if you're not that far off the ground, okay? Just because of your mass, all right? So if I'm looking at my initial mechanical energy, okay, I've got my initial potential plus my initial kinetic, okay? And when I'm going over the bar, we said I had only potential. Okay? I mean, in the truest sense, we would also have a little tiny bit of kinetic as we've been moving forward, but we're simplifying a little bit here. So there's no final kinetic energy on this question. All right, so I'm trying to find the maximum height, so I'm going to put in my formulas here. M times G times H plus 1/2 mv squared equals M times G times H final. Okay. I'm looking for H final, so what do I have to do with the M and the G? Divide them over here. Okay, do I need all those masses? Not this time. I'm not solving for an energy type. I'm solving for one of the variables that's part of it. So no, I actually don't need the mass for this question, so I can simplify that as well. I'm going to have 9.81 times my initial height, 0.850, okay, plus 1/2 times the initial speed, which was 8 squared divided by 9.81. Okay, 4.11 meters. Okay, that is at least a full meter higher than I've ever seen anybody pull. Okay, I coached track and field in high school, okay, for 20 years. I think the best I ever saw was 3.15 meters, which is 10 feet. Okay, and the only thing that kept them from going higher was they didn't have a longer pole. Okay? They only had a 3-meter pole. Right? If you're going to do the 4.11 meters, you need the 4-meter pole. Okay? Everybody with me there? That's really high. Really high. It's ridiculous. Okay? That someone could pull all that out. Okay. Questions on how that works? Okay, are we feeling a little more confident with the law of conservation of energy stuff? Okay. That's not what I want. Okay, I want you to try that one. I'll make it a little bit bigger. Okay, so for this one here, this is the situation we're in, okay? You got a roller coaster, starts from rest. Okay, so VI equals 0. That makes things easy because its kinetic energy then at the top is what? It's not moving, it has no kinetic energy. Okay, we're looking for the speed of the roller coaster when it's 4 meters above the ground, so over here. 4.0 meters. Up here it is 12.0 meters. All right. So the mechanical energy is conserved in this question. The initial mechanical energy equals the final, okay? But initially we only have potential energy. At the end we have both. How do I know we have both? First off, it tells me it's 4 meters above the ground, and the second thing is it's asking me to calculate how fast it's going. It obviously has to be going faster than 0 because it's lower. Okay? Some of that potential has to be converted into kinetic. All right, M's in every term, so I can cancel it off. I need to get VF by itself, so I'm bringing GHF over here. So I'll have GHI minus GHF equals 1/2 VF squared. Divide that by 1/2 and square root. Okay, and I've got VF Okay, so when I plug in my numbers, that'll be 9.81 times 12 minus 9.81 times 4 divided by 1/2, which should give me 13 meters per second. So this is like the little kiddie roller coaster. That's not very fast. Okay, if you were on that, you'd be like, "Whee! Yay!" And you'd be really bored. Okay, because it wouldn't be very fast. All right. I changed my mind. Yes, that is the one I want to do. Okay, so this one's a little bit work energy theorem and a little bit of law of conservation of energy. It actually integrates both concepts. Okay, so I'm going to have you guys try that one as well. Now, the one thing we have to know about this is that the height of the arrow is not going to change. I know that's a bit artificial, okay? But in shooting the arrow from the bow to the target, there's no change in height. Okay, if we pull back on this bow 0.30 meters, what are we doing? Giving it potential energy because we're doing four-letter word work. Yeah. Okay. So the work we do, okay, is going to be equal to the kinetic energy that the arrow will have when it leaves the bow. Okay, so it's work energy theorem, but we also have to understand that that energy is conserved along the flight of the arrow as well. Okay, so if I can do this, force times distance, okay, 1/2, okay, mv squared, I should be able to calculate how fast the arrow leaves the bow and thus how fast it's going when it hits the target, assuming there's no friction or anything like that. Okay, so all I have to do is solve for v. I divide both sides by 1/2 of m and square root. Okay, and that'll give us 12 newtons times 0.30 meters. Okay, divided by 0.5 times the mass, which was 0.45. Okay, so when we do that, we should get 4.0 meters per second. That's not very fast for an arrow. That would easily be one of those ones where like the ninja could grab it out of the air. Did you ever see that in the Mythbusters? Okay, where they were like shooting arrows at this guy who said he could grab an arrow out of the air as it was flying towards him. And he did it. I couldn't find it.